All right, today we are here to talk about M1 Ultra and a little bit of the implications. Is this particular design a big shift in the industry? What does this mean for the next purchase for your company or for your organization? So let's dive into what that is going to be all about. Today, I want to talk a little bit about a few different things. And specifically, I'm going to focus on the chipset side today. I know that the announcement had a lot of discussions around other products, but today I want to focus on the chipset. So I hope that you can, if for everyone who is joining us today live, welcome. I'm Dr. Ed. I'm just a geek kid who grew up in the northwest side of Calgary, the northeast side of Calgary. And we're in the community right beside Pine Ridge. And you don't need to be a historian to know why this particular community is called Crime Ridge, nicknamed Crime Ridge. And so, yeah, I've grown up and I've seen all different aspects of Calgary. And today, I want to talk to you specifically about this aspect of creativity that I think is really important, that's applied to chip design, but also applies to everything that we do, right? Everything that we do in our own work. There's some key lessons here that I think we can all take forward in whatever work that we do. And so, if you are ready, we're going to get started. Now, the first thing I want to talk about is that I feel that for the majority of consumers, I believe we're well beyond the point where, well beyond this threshold where for most consumer applications and even business applications, the individual processor itself has enough compute power, both for graphics and for the CPU power, to not need to go and buy these things all separate, like a separate card for graphics or a separate card for your processor. And that's one of the big shifts that is happening right now. Yet, of course, one of the big things that we need to talk about is integrations. Integrations with any new processor has always been really difficult. They've tried to make it easier in this case with the Ultra by combining it as looking like a single processor. And so dealing with a lot of the complexity in hardware as much as possible. And I want to share just a little bit of what architect Demi Lee explains about how what are some of the challenges that she's experienced using just the M1 for architecture software. So if you'll join with me, we will.
I needed an online store for my jewelry design business, so shop here.
Okay. Oh, it didn't go. Okay. Okie doke, here we go. And thank you to everyone who's joining me.
I feel like it's actually a really good deal, especially if you compare it to the previous Mac Pros, which cost a lot more. Now that we have all of these SoCs with all of this GPU and CPU at this price point, I really hope that there's going to be more software optimization, because I think a lot of industry professionals would want to take advantage of these computers, because the problem with the M1, even though it was, at this price point, I really hope that there's going to be more software optimization, because I think a lot of industry professionals would want to take advantage of these computers, because the problem with the M1, even though it was, already quite powerful, the problem was always the software optimization, especially for architects. And what's really incredible is the design, literally just a aluminum box, and it has the capabilities of a full workstation. So you can put it in your backpack, you can put it in your suitcase, And as long as you have a monitor and a source of power, you basically have a full portable workstation for you with loads of connectivity. On the back, you have 4 USB-C ports rated Thunderbolt 4. And you can connect up to 4 5K monitors and an additional 4K TV screen. Who really needs all these monitors? I have no idea, but I mean, it could come in useful.
Okay, so oops, what happened here? I'm gonna, give me a second. Great. Cool. And so we are gonna back up a sec. All right, this way then. Okay, so one of the things that Dami mentioned was that integrations is still difficult, but really, like, for most of her purposes, like, it wasn't the graphics actually that was the limiting factor for her. What was the limiting factor was essentially the architecture itself, right? So the design of this software to work with the M1, and that's probably just a matter of time. But I do imagine, like, this is going to take a rethink for software development in general. How do we make it work with any type of solution? And so that is, like, always a factor. Like, always, like, integrations. I think one of the big things has been Apple using Metal, and they're not, like, how close does it follow the OpenGL or DirectX? Like, they all have their own different graphics standards, which has made compatibility challenging. So, but really, what we are talking about here is the competition between the reduced instruction set computing and the complex instruction set computing of a lot of the Intel PCs. This is the big shift that we're seeing right now. So reduced instruction set would be like your ARM instruction set, and the complex instruction set would be very similar to the Intel instruction sets. And these differences relate to complexity. And I'm going to try to explain that today. I'm going to give you a high level. I won't go into all of the details of ARM architecture, but I think it's important for you to know what the differences are between these, because this particular lesson about complexity and how, as you scale, essentially the complexity just increases exponentially, is a very important lesson that you need to consider for any type of work that you're doing for your own business or for your own organization. What is that level of complexity? So here we go. We're going to launch, let's do this one. So this is a super, super old video, and it's going to talk to you about specifically what is done in this how do I describe this? Like, what is done in this space related to complexity? And I think that it's a very interesting look back at people who are talking about ARM and how do they explain it in the media. So it hopefully, like, this one was designed for, like, news media. So hopefully, and it was designed for mass consumption. So hopefully this is a good intro way of doing it. We shall see. Okay, I just need a second to load this up. Here we go.
While changes in architecture trailed behind. The new architectural design used in RISC, or reduced instruction set computers, uses simpler instructions requiring fewer machine cycles. In the early 1970s, IBM examined the kinds of operations most commonly carried out by a complex instruction set machine, and found that only about 20% of the simplest instructions represented about 80% of the processing time. RISC architecture relies on these simple computational elements to execute most of its operations in a single cycle. While RISC has made few inroads in the market, at least one major company, Hewlett-Packard, demonstrated its confidence in RISC by introducing a whole line of RISC-based machines as the next generation of its high-end computers. All computations except load and store take place in the data path. Inline subroutines can be called up for complex functions, and assist processors operate when required for floating-point arithmetic and graphics. The special nature of RISC design makes it well-suited to engineering and scientific applications, where instructions of 4 bytes or less can be executed in one cycle. But while such applications demonstrate the advantages of RISC, some critics contend that the speed gained by reduced instructions could be wiped out by the longer data paths and by the need to accommodate complex functions.
All right. So, I hope that that particular comment makes sense. I know that it's not may not be the simplest thing, but I think the key thing that you're trying to understand is the reduced instruction set. So what do they mean by reduced instructions? So really, this complexity is what they're trying to reduce. So they have the way that I would describe it, and I think that Gary Explains is going to explain this better than me. Actually, maybe why don't I show his first? I'll show his example first, then you'll get an understanding. So Gary Explains, he understands the architecture for chips really well, and I think he does a good job of showing the difference between reduced instruction set computing and complex instruction set computing. So why don't I get that one started first?
Now, the argument was put forward like this: if you can have a less complicated set of instructions, then designing a CPU will be easier, and if it's easier, it will therefore be cheaper, and if it's cheaper and easier, it will also happen quicker. And
whether you're building dynamic network models or forecasting real-world behavior, Neo4j's new...
One of the fundamental ideas behind this was that every instruction can be executed once per cycle. So we talk about clock speed. You know, my CPU is clocked at 2.2 gigahertz or 1.3 gigahertz. And so every time that kind of wave of the frequency happens, you can execute one instruction. That's the idea. And in a complex instruction computer, that's hard, because each instruction is doing so many things. You have to wait 2, 3, 4, 5, maybe more cycles for it to get around to do all those things you've got to do. In a RISC setup, the idea is that every time you execute a cycle, you can actually execute an instruction. So once you start to think along the lines of one instructions per cycle, there are some other assumptions that you can make. And I'm really talking about some of the things that David Patterson wrote when he proposed the idea for the RISC-1 and the RISC-2 processors. We find a similar thing in kind of the MIPS processors that were being developed also in that same time frame. One is, as I said, that you execute one instruction per cycle. Another is that the instructions actually have a fixed size in memory. And that means that it's easier to decode them and easier to kind of send them down towards the pipeline into the execution, because you're dealing with the same fixed amount of data. In something like x86, the instructions can actually be variable length, up to, I believe, 15 bytes long. And you don't know how many bytes are related to this instruction until you read the first bit of the instruction and then see what you need to read on afterwards. When you have a fixed instruction size, you can always take the same block and you can very quickly process it, because you know exactly what you're grabbing at each time. And probably the most fundamental difference about RISC versus CISC is that RISC does not do any operations directly on memory. What do I mean by that? If you, for example, have the number 7 in address 100 in memory, and you want to add 1 to it, in x86 and other CISC kind of instruction sets, you can say add 1 to the number that is in address 100. Now, to do that, the CPU first of all has to go and fetch what's in address 100 and bring it into the CPU. It then has to add 1 to it, and it then has to write it back out again. And it does all that following just one machine code instruction that it read. But it obviously has to do 3 separate things: the fetch, the add, and then the put back. Now with RISC, what you actually have to do is you have to have 3 instructions. The first instruction says, go and fetch that memory. The second instruction says, add 1 to this register where that memory content was placed. And the third instruction says, please write that back out now to the main memory. So what would be 1 instruction in a complex instruction set computer is 3 instructions on a RISC computer. And the idea being that each one of those instructions can be executed every cycle. So because they're small enough, because they're reduced enough, because they're simple enough, you can execute one every cycle, and you don't have to worry about trying to work out what all these other things I have to do to get this thing to actually complete.
Okay, so I am hoping that that makes some sense there. And the key here is when it comes to this notion of the cycle and the length of the instruction, right? So there are ways that you can do it. So one is like you can have a very complicated instruction set. And so I'll show you the example. It's like if this instruction can be any arbitrary length, I could have many different. So the first step is how long is it? The first question that you need to answer is how long is this instruction? If the instruction is super long, then you have to spend time for every clock cycle. That consumes power, that makes things slower. That's one of the reasons why the complex instruction sets are harder to do. They take more power, they're a little bit slower. The other was specifically about the clock cycle. So with every clock cycle, which means like if it's like 3 gigahertz, it's running at that speed. For every one of those clock cycles, you want to be able to run one instruction. So one instruction here, one instruction here, one instruction here. You don't want a operation that actually takes multiple clock cycles. So let's say it takes 3. You don't want something that takes like, oh, this thing, I'll come back to you. I'll come back to you. Well, when will you come back to me? When will it be done? So it's this forcing of it, forcing the simplicity in the processor that makes a big difference. Okay, so that's one other aspect that is very important to consider, is how complex it is, and this relates to a lot of the things that you do in in life, right? Like, so every single step that you take, if you have to do one extra step for it, it makes everything more complicated, and that's really what we want to avoid here. And so really, when it comes to this approach, I see it as, well, what's the implications of something like this? Well, for most consumers, like I said, I think that moving towards having everything internal, like one of the things that Gary mentioned was that for doing an operation, like going into memory or going to the disk, for example, is extremely slow. And the reality is, it is a extremely slow operation. And in RISC, that's penalized with multiple instructions. And that's a good thing. Like nowadays, I think today, that story is a little bit different. And the reason it's different is because the content, more cache is available in some of the modern processors, so you can do more operations directly on the chip. And so that is giving some huge efficiency benefits. Oh, you need to write something. Okay, well, we'll put it into the cache. We'll make it really fast for you. We can do that as part of the reduced instruction sets that are available. But following this hard rule that everything must fit within one clock cycle is very powerful. It gives you a lot of opportunities, some advantages. I think that really, for me, one of the big things that I found interesting about it was the power use, how much lower the power use was for roughly the same equivalent performance of some of our highest end graphics cards or highest end desktop work processors. I think that this is going to have some big implications for areas that where power isn't easily accessible. Like you wouldn't ever really think, oh, I can run like a PC, say off a solar panel. But I think with devices like these, as risk improves, I think it's much more reasonable to have a decent computing experience on a device that consumes next to no power. And so, okay, so the next part I want to talk a little bit about is, well, the way that this architecture works is by combining two different processors. And I want to talk a little bit about that. Is, well, how does that work? Can you combine 4 processors? Can you combine 8 processors? Like what? Like are we going back to cores now? Like it's kind of confusing. And so there's another channel called Tech Potato. He explains it, and I'll run into that now. Bring it up.
Let loose its M1 Ultra Silicon.
So
This new beast
this.
has more memory bandwidth than we've ever seen before in a CPU. What's your minimum specification? Well, shucks, the cloud is here, but which cloud do you trust? Manage your infrastructure with Linode, the biggest independent cloud services provider. Linode offers... So you won't get a 4 version. What you might see in a Mac Pro type situation is either a higher TDP model or a dual socket model. How exactly that would work with having GPUs on both dies, and then perhaps having additional AMD GPU
Okay, sorry.
single die for these M1 Max new Mac Pro based on its own silicon. Now, based on these numbers, as I said, it kind of sounds like Apple has no more need for AMD in that market. I really have to wonder, though, whether that Mac Pro market is still optimized for x86 and optimized for OpenCL, and whether they would really take to M1 silicon in that way. People have said, well, does this look like that Apple could put 4 of these together in a single die, 4 of these M1 Maxes, and make that the Mac Pro? There isn't the connectivity to do that. 2 is literally the max going by the die diagrams. So you won't get a 4 version. What you might see in a Mac Pro type situation is either a higher TDP model or a dual socket model. How exactly that would work with having GPUs on both dies, and then perhaps having additional AMD GPU, physical AMD GPUs inside, I've got no solid clue. I mean,
Okay, so that's one example. And I think that, like, really, that's just like a hypothesis that they couldn't combine it. Really, I do think when it comes to the creativity, I think the key here is that, I mean, why couldn't we have done this with Intel processors? Why couldn't we have just made a bigger and bigger chip? Why couldn't we have achieved that efficiency a long time ago? And I think if you look at the reasons behind this is, well, one is heat. It gets ridiculously hot. And that's one of the big factors. The other is, what do we do? Like, in terms of manufacturing, there's another factor, which is the yield, right? Because the more complex or the more transistors, the harder it is to manufacture. Like, the more likely you're going to have a defect, you're going to have to throw the whole wafer away. But when you have a reduced instruction set and everything is simpler and you're just doing the same thing over and over again, that's what they're really repeating here. That's where the main advantage comes from, is this movement towards a simpler design, a simpler architecture, just repeating the same thing that you know works over and over and over again. That's what the core of this chip is. So I think that really, to improve efficiency, you may need to start looking at changing the architecture. But before that, it's like, well, what can we do with the current one? And so they're essentially arguing that you've essentially reached the limit of where you can reach with this. So I think that that's almost all that I have for today. There's one more that I want to cover, which is Gary Explains has a good one about the chiplet design. This is not unique to Apple specifically. This is something that has been discussed among Intel and a number of companies already. This notion of chiplets. And so I think that understanding chiplets will help you understand a little bit of where the future of this is headed. So I want to move into that next. Okay, so when it comes to chiplets, just think of them as like, well, instead of having a single processor, having a single processor and then having a bunch of cards that you attach to it, like PCI Express cards. Chiplet design is about combining that all at the chip level. That's the big trend that's happening right now. So yes, we're getting integrations, but instead of plugging in a graphics card, you're building it into the design of the chip. And that level of integration, that close integration at the chip level, is very significant in terms of what we're going to expect in the future for this. So let's see if we can dive into this. Oh. Sweet. So then we'll talk a little bit about performance, and then we'll there.
Power efficiency cores, so that's double what you find in the M1 Max. It's also got up to 64 GPU cores, that's double again of what you find in the M1 Max. And you've got 2 neural engines, you've got 2 video decoders, 4 video encoders. In fact, everything you look at it is double what you find in the M1 Max. And there's a reason for that. And the reason is the M1 Ultra is 2 M1 Max processors glued together. It's not quite glue, obviously, it's a bit more technical than that, but you basically get 2 M1 Maxes inside of the same physical processor. So why is that, and how has Apple done it? Now, hopefully you had a chance to watch my video about how Intel has joined the RISC-V Foundation. And in that video, I mentioned how Intel is going to concentrate on providing chiplet services as part of its Foundry services. Now, what do we mean by chiplet? Well, there are physical barriers, physical limitations to creating bigger and bigger pieces of silicon with all the chips stuff, the transistors etched onto it. Do watch my video on how microprocessors are made. Now, the M1 Max has 57 billion transistors on it, and there are problems in trying to grow that to bigger and bigger. However, there's nothing stopping us from taking smaller pieces of silicon that have already been etched with all the transistors on them and joining them together with a kind of an internet, and they're called chiplets, and that's what Intel said it's going to be offering as part of its Foundry services. And also recently we had the launch of the Universal Chiplet Interconnect Express, UCIe, which is a standard supported by Intel, AMD, ARM, Qualcomm, Samsung, Google, Microsoft, TSMC. Basically a universal way to take chiplets, these bits of silicon, have them connect to each other on the kind of the physical package, and then that allows you to build up more and more complicated systems. And you could even have chiplets from different manufacturers and kind of join them together. Kind of think about PCI Express, but not on the motherboard and not with slots and big cards, but all the way shrunk down to the inside of the actual chip packaging.
Okay, that's really important. So this chipset, right? So we used to have PCI Express. We used to have a bunch of cards that we would insert, one for your graphics card, one for your sound card, you name it. And nowadays people are saying, no, what if instead of having PCI, we had a UCI, which was this universal chipset integration interconnect. And so this is a trend. And I think that this is the key trend that I don't see covered in many other channels. Like the fact that we're doing that integration at the chip level and we are potentially building ways that other manufacturers' chips can be directly integrated, means that you could potentially have a like an Apple M1 processor, but I want like NVIDIA's chip in there as well, and you would buy a package that contains both of them. And so this tight integration, this tight coupling, is what gives you the real strength of this tool, and why I think that the M1, especially its direction, is particularly interesting. If you look at just the like, you ask the question, well, okay, great. So what's the big deal? Like, what is changing here? What is going exponential? All you have to do is just look at like if you looked at what is improving very quickly, faster than Moore's law, and Moore's law is this doubling of the number of uh, transistors, I believe, every 2 years. Something is moving very fast, much faster than Moore's law right now, at least in the chiplet design. And where is that? Well, let me show. So let me see if I can find it. Okay. So if you look at just the main page here, I think that this one has most of the stuff that I wanted to cover. Okay, so really what we are talking about here is, yes, the CPU cores, right? The central processing unit cores, they have been increasing from, say, 6 to 8 to 10, and then ultimately to 20 with the Ultra. So that's been increasing maybe 2 times, 3 times. But look at this one. Look at the number of GPU cores. So what's going on here? So we're going from 4 cores to 64 cores. So now we're going exponential here, right? So this is the one that is growing. The algorithmic units, arithmetic logic units, ALU, is like increasing exponentially from 512 to 8,192. And you can also see that the transistor count in total is increasing substantially. So you went from 11 billion to 10 times that, right? 114 billion. And this is all within the span of about a year, right? So this is way faster than Moore's law. And so the discovery of this ability to add more and more transistors using a totally different architecture is the key here. And so I think that the way I see this is that as more and more, like if you think about, there's 2 different types of instructions, right? So we talked about like the complex instruction set, CISC, and we talked about the reduced instruction set computing. Yes, there are those 2. However, there is also the chiplet design, right? So now what they're doing is like graphics. Think about graphics. Like, what is graphics? Graphics is mostly you take this entire, all the pixels of the screen, and you're doing operations. Or you're doing some 3D model and you're trying to turn it into pixels in the screen. This is what graphics processors do extremely well. So instead of doing everything one by one, like one pixel, then the next pixel, you could process all of those at the same time, simultaneously. And so you will see like they have thousands of cores or tens of thousands of cores, or each one maybe processing one small portion of the screen. And that makes the rendering of graphics, 3D graphics, extremely efficient. And that's what you're looking for in a graphics processor. You're just looking to split that up into as many different processes as you can. Yes, for the computer, like the CPU stuff, you're doing more complicated things. You need to go one by one. You may not like need as much acceleration, but for the graphics, you absolutely do. And as we move and discuss a little bit more about the metaverse and how 3D graphics is just going to be a part of all of the experiences that we have, the expectation is that you can have good graphics on your processors built in. And I think that we're getting to that point where, I mean, if you can reach the level of some of the highest end graphics cards and some of the highest end processors, we're getting to a point where people would ask, well, why? Why would I go out and buy those graphics cards? Why would I go out and buy those for your average consumer? Of course, there will be people who will be enthusiasts, like there are people who are wanting to get the latest and greatest. I can still imagine them going for dedicated hardware because that's going to perform better at the task that they're trying to achieve than most. Like speaking of dedicated hardware, I would be remiss. We're on the AI parenting channel if I didn't talk a little bit about AI. And so there have been benchmarks done of this software on AI tools, and AI is very similar to the graphics processing in that what you're doing with deep learning is you're taking a huge data set and you're trying to create models from them. And the way that you can do that is you can parallelize it, you can split it among a number of different cores. And so they benefit from the graphics cores that are available. And I know that there are some cores that are specifically designed for AI. And there's also chips from companies like NVIDIA that specifically cover the development of AI. And so, like what I've read so far is that the M1 isn't quite there in terms of the AI performance of, say, a dedicated chip, but it also it's also multi-purpose, right? So it's kind of amazing what it's able to do at this current point. And so I see that as something that is quite interesting. There have been people who have done like benchmarks on all of these things. I mean, the biggest factor that I see right now is the cost. At $4,000 for I don't know, like everything's getting more expensive these days, sure, but that is a lot more expensive. But I envision that it is really like, yes, things start out really expensive, but it's just a matter of time before everything just becomes cheaper. This is the way that the industry has been working for years, and so there's implications for that, and I think that it's very exciting. It's a very exciting time to be seeing and leveraging all of this this ability to access this much technology and be able to have it in the hands of most consumers. Most consumers may not go out and buy a really extreme gaming rig, but they will certainly buy a computer. And if they buy a computer that has all of that integrated, it means that things like really amazing graphics will become accessible to the masses. And it allows us to do things like what I'm going to be talking about a little bit more in the future about doing more live stream cinematography. And so, if you found what I spoke with helpful today, please go and check out the site, or leave a comment. Just let us know. Well, what did you find? What was helpful for you? And feel free to go and check out the site aiparenting.live. This is where we keep a lot of like our email contact. We have courses that are specifically related to AI. That's all covered in aiparenting.live. And I'll put it into the chat as well. And so really, I want to encourage you, like, think of this as like, this is a great time. The amount of computing that you can get access to for the price range, especially if you go for some of the lower ones, like the M1, it's crazy. Like for me, for my own work, doing a lot of video that is real time, I have found that I've gone from like 100% CPU on a Core, I think i5, to maybe 20%. So like I'm 5 times faster on one of these M1 Pro processors. And I think that's pretty typical. Like people are seeing like, wow, like what is the difference in performance that you're experiencing? I'm seeing something around 5 times. Maybe you're seeing less, maybe you're seeing more, depends on your particular application. But I do think in terms of the graphics and the performance, like just what you can get from a regular computer is quite fascinating. So that's all I have for today. Thank you very much for joining us. Go and visit aiparenting.live if you want to learn a little bit more about the work that we do. Basically, we're trying to help companies compete in the global marketplace. And part of that involves knowing about AI. And it also involves like training also our kids about about AI. It's an area that I'm really passionate about. Like I say that in China, they're teaching AI in kindergarten. They don't allow kids to play video games. Like online video games are banned across the country from Monday to Friday. I think you can play like 3 hours on the weekends. And they are also restricting social media from 10 p.m. till 6 a.m. every single night if you are under the age of 14. So these rules are there because they know what's going on, right? They're aware of the impacts that always on video gaming and always on social media is having on people and societies on mental health. And I think that we have an opportunity to take advantage of the same things. It's something that I'm advocating for today, and I think I will continue advocating for. We are in this new world where our data is the new vote, and learning about AI and programming is the new law. And we need to understand that this is not just a technology that we're talking about today. This is our future. This is our democracy. This is a lot of things. So the more that we understand what's under the hood of the tech, the better. Thank you. I will see you guys again probably next week.